Welcome to CyberSecurity from Scratch, Technical Foundations, Episode 4, Practical Cryptography. We're going to start this episode off with some of the foundational cryptographic concepts, namely encoding, hashing, encryption, message authentication codes, and digital signatures. And then we'll get practical by discussing some of the tools that we use to create some of these cryptographic functions. And then finally, we're going to have a little fun at the end and do a little capture the flag password cracking. Encoding is a concept that often gets conflated with encryption, but they're two different things. Encoding simply means that we're changing the format of data from something into something else. Say, for example, that you have an image file and you want to be able to send it over a text-only channel. Well, unfortunately, the bytes that you have won't fit into just normal text characters. If you try to send it that way, the data stream will interpret the non-text characters as, in air quotes, bad, and then the whole file will be rejected. And so we have a technology called base64, where basically any arbitrary binary data gets re-encoded as text characters, so you can take those image files and send them in text-only channels. This is used in email attachments, which are often in this format, because you can encode the entire email as text characters and then depackage it as whatever arbitrary binary is necessary. To identify base64, look for the equals character at the end of the string, which is usually used for padding. This doesn't always happen because sometimes the string doesn't need padding, but if you see the equals characters, that's a dead giveaway. Now, this is really important for pen testing purposes and for vulnerability assessment, because often developers will encode something in base64, like a cookie or something like that, and assume that because it looks like a bunch of gobbledygook, that nobody can read it. Well, you can. It's not really encrypted, so anybody who can plug that into a base64 decoder is going to know exactly what the cookie says. So it's quite common to find that important credential information is exposed because a developer mistakenly put it in base64 format. There's a base64 tool that comes along for the ride with Linux, and we're going to use it now to take a look at encoding and decoding base64 information. So first we have a test file here that just has a basic message in it. And if we want to see what that looks like in base64, we can try out our file. If we want to, this just renders it to the console. So if we want to pipe that to a file, we can then do so. And then we can see our file here has the same data. And if we want to decode it, we can see it right there. So this is nice and easy, both from a pen test perspective and from a developer perspective. If you're developing, it's nice and easy to sort of sanity check the files and data that your code is producing, because you can decode them or encode them and so on and so forth. And it's very easy to hook this into bash scripting. But then on the pen testing side, it's very nice because if you get base64 information out of some of your scanners, you can pipe the data right into these tools and see if there's any potentially readable information, all within a nice bash scripting framework. It's very convenient. Hashing is a strictly one-way operation where data is fed into the hash function and a fixed value comes out. So for example, with a particular hashing algorithm, the output of the hashing function might be exactly 32 characters, regardless of how big the data that's fed into it is. And one of the key concepts is that you absolutely cannot reconstruct the original data from the hash. Now you might be thinking, why is this useful? You feed data into it, you can't figure out where you came from. Turns out that for passwords, this is vital. So say, for example, that you need to store passwords in a database, and so that when a user submits their username and password, you have something to check against. Well, you don't actually want to store the password in the database as just raw text, because if somebody's able to get into the database, and you kind of assume that somebody will get in somehow, then they have everybody's passwords and they can get into your system, they can use those passwords in other systems. It's just a mess. You don't want that to happen. So what you can do then is you can hash the password. You have this one-way conversion and then store the hash value. And then that way, whenever the user tries to log in, the password never being stored is fed into the hash value function, and then the two hash values can be compared, the one from in real time where the user is trying to log on, and then the other from the database. Now, the cool thing is that attackers, if they get these hashes, will have to spend time trying to guess the password values. And then that way, once they finally guess a password that matches with the hash value, they could then turn around and use it. But that takes an enormous amount of computational resources. Now, one technology that was introduced to try to get around this is to have what's called a rainbow table, which is essentially just a lookup table that compares hash values to original passwords, so that if you have a hash value, you go to the rainbow table and figure out a password which would have resulted in that hash. Now, to counter this, in the modern day, we store salted hashes, where instead of just passing the password into the hash function, we also come up with some random string that gets added to the password, and then the two of them together get fed into the hash algorithm. And then that way, you can't really have a rainbow table anymore, because you'd have to have a rainbow table not only for all possible password hash values, but all possible salt values combined with all possible passwords. And there just isn't enough storage in the world to store all of that. So you really don't have the ability to do a strict rainbow table lookup. So you can still possibly crack a salted hash in the modern world, but if it's been done with a secure algorithm with a truly random salt, then you have surprisingly good security on that capability. Then the attacker needs to have some custom hardware or something like that, which will allow them to crack the hash. If they're just using desktop commodity hardware, you could reasonably expect the heat death of the universe to happen before the password is cracked. Another thing that hashes are vital for is supplying checksums. So say, for example, that you're downloading a file and you want to make sure that you got the correct value for that file, like that nobody intercepted it and modified it. So what a website will do is publish a hash value or a checksum for the file. And so once you download the file, you compare the checksum of the file you have versus the checksum supplied by the server. And if you come up with the same value, you know you have the same file. Hashing algorithms come and go because inevitably we eventually find something somewhere that's a problem with the hashing algorithm that we're using. MD5 used to be considered secure and it used to be very popular. However, it's pretty vulnerable to cracking. It only produces a 32 hexadecimal character hash, and there's a number of weaknesses that just make it fairly easy to crack. You'll often see it in pen test training and capture the flag exercises precisely because it's easy to crack, because it's easy to sort of recognize that this is an insecure hash, and then you can use one of the many hash cracking tools that we'll look into later to crack into it. Now, to give you an idea of how insecure it is, it's often possible to simply take that 32 hexadecimal character hash and plug it into Google and come up with a value. And in fact, this often is the solution in some of the easier capture the flag exercises. You get the hash, plug it into Google, and you get the password out. SHA-1, or the Secure Hashing Algorithm 1, was the successor to MD5. However, it didn't really live up to its name and is no longer considered a secure hashing algorithm. So now it's been deprecated, and the vast majority of applications should have moved off of it by now. SHA-2 and SHA-3 are more recent algorithms which are widely recommended. Something to keep in mind is that depending on the regulatory framework that governs your system, you will almost certainly be required to use one of the specified portfolio of hashing algorithms. And there's still some settings within SHA-2 and SHA-3 that will determine which version you should be using. So if you work in an industry that is governed by a regulatory framework like this, make sure you know what hashing algorithm you're supposed to be using. The National Institute of Standards and Technology, or NIST, also provides recommendations on which algorithm to use. Let's see an example of hashing with real pen testing application. So the Linux etc password file is normally used to define users, and you can see from there all the users that are on a system. Most of the time, you don't have your passwords hashes stored in this file. Modern Linux uses an etc shadow file to stash these. However, for legacy purposes, you can have the hashed password in the etc password file. And so if a user is able to, for whatever reason, get the ability to write into that file, they can place in the hash for a new user, and then suddenly they can log in with that user and have those permissions. So to generate said hash, we use OpenSSL, and we pass this password argument. We tell the salt of hacks and the password of 123. So we can see here the hacks is the salt, and here is the hash for pass123. We can also, if we have this hash and we want to figure out sort of what the hash might be, we can use the hash ID command, and then say we'd stored this hash into the file password hash. It will analyze it and give us some guesses of what the hash is. So this is really useful for both the OpenSSL command for creating your own hashes, and in the hash ID for if you happen to find a hash, trying to figure out what it is as a first step to potentially cracking it. Now, you can't just plop this value all by itself into etc password. There's a few other things that you need to do to format it. But when we get to Linux privilege escalation, we'll talk in a little bit more detail about how etc password is structured and the way that different attacks can be rendered against it. Now, on the blue team side, if you're ever looking at an etc password file and you see a hash like this in there, that's really, really bad. That means that somebody is probably in your system doing bad things, or somebody has grossly misconfigured your system. Either way, it's very bad, and you should do something about it immediately. Just as we have checksums to provide integrity for files that we're sending across the network, when two parties are sending encrypted messages with each other, they want to make sure that the messages were not modified en route. And the way that we do this is we use what's called a message authentication code, or a MAC. The idea is that both the sender and receiver of the message, as part of the initial exchange of whatever communication mechanism they're using, will agree mutually on a secret key that both share. And then what will happen is that key will be used to generate a code so that both the sender and the receiver can tell that the message was not modified en route. Now note, this doesn't provide non-repudiation. Both parties have the key. This is simply a function of the communication mechanism to make sure that the messages were not modified or unintentionally corrupted en route. We often will call these message integrity codes as well, because we also use the acronym MAC for the MAC addresses that we have in networking. And having two MAC acronyms in networking already, it's a little confusing. One of the key objectives of secure communication is non-repudiation, or to say that the person who sent the message can't then later say that they didn't send the message or that it was altered. You have proof that the message is exactly what they sent. And the way that we do this is with the digital signature, which is a short code which provides that level of assurance. Now, the way this works is the signature is produced with a private key, which only the signer possesses. No one else in the world has that, and it's able to compute this signature value. Now, there's also a public key corresponding to it that is used by everyone else to validate that the signature is correct. These are not the same thing, so that someone who has the public key can't then spoof the results of the private key, but they can verify that the private key produced the value that they believe it was because of the signature. Now, the way you make sure that the public key is known is often your organization will distribute the public key and will in fact sign it by another authority. So just for example, in secure corporate environments, often everybody has their own private key, which they use for signing documents or whatever. And there's a central authority which is distributing out both those private keys as well as public keys, so that when you're receiving a message, you can check with that authority and say, what is the actual public key for this person, and make sure that you should trust the message that you're getting and the signature that comes along with it. When a public key has been signed itself by a digital signature, this is what we refer to as a digital certificate. This is proof that the public key is authentic to a party. So to see how this is valuable, let's take the example of a company. So let's say they sell futons, for example, and they open a website, and you want to make sure as a user that when you're communicating with that website, you are in fact talking to whatever the futon company is. So the way this works is a certificate authority will issue a digital certificate for the futon company, and you know for sure that the authority of the digital certificate is real, because the certificate authority is one of several organizations that are recognized worldwide as having the authority to issue these certificates. So essentially, this is the web of trust on the internet, where there's a handful of companies which have the trust and authorization, which is programmed into our web browsers so that any certificates that they create for other companies or websites are recognized. And so there's essentially just a flow down of trust from those certificate authorities to the individual businesses with which we're doing business. Encryption is a form of encoding where, instead of like base64, where anybody can simply decode a message just by knowing the protocol, you need a piece of secret information which can control the number of people who are able to decode and read the message. There's a couple concepts involved in encryption. First is the idea of plain text, which is simply the unencrypted information. Next, we have ciphertext, which is the message after it has been encrypted. Then we have a key, which is an enabler of the cryptographic algorithm. And then we have key size, which is how many bits make up the key. And this provides a large measure of the security of the algorithm, because the best secure algorithm in the world, if it has a small key size, it just makes it a lot easier to guess the possible combinations. But if you have an unfeasibly large key size, it makes it a lot harder to iterate. Now you'll note when I described the key, I didn't say that it was secret, and I didn't necessarily say it was the information used to encode or decode the message, because it's not always true. For symmetric key encryption, which is where you have a single key that both the sender and receiver of a message have, this is the case where it's a secret key, both people have it, and anybody who has that key can read the message. However, there's also asymmetric key encryption, where not everybody has the same key. Symmetric key encryption is the quite literally ancient form of encryption, where both parties involved in the message exchange have the same encryption key. The first party will perform some mathematical operation with the plain text and the key, and then the receiving party will just do the exact mathematical inverse of whatever the encrypting party did. Now, in the digital age, the data encryption standard, or DES, for a while was the standard. However, in the late 90s, it was demonstrated that, admittedly with a bunch of custom hardware, you could crack a DES key in less than 24 hours. Not a lot of people could do it, but it's not really all that secure if somebody can get into your stuff in less than 24 hours. Triple DES is a version of DES which was developed after this, which is practically secure in the sense that the vast majority of attackers just don't have the resources to actually crack it, but it is possible, so we don't really use it for things that need to stay secure. AES, or the Advanced Encryption Standard, is the modern standard which has superseded DES, and it's used globally as an official standard. Both AES and DES are forms of block ciphers, where whatever the plaintext is chopped up into little boxes as big as the key. So for example, if your key is 128 bits, then your plaintext will be chopped up into segments of 128 bits, and then both will be fed together into a function which produces some sort of output. Now we're going to get a little bit into the weeds on how these block ciphers work, because when you're configuring a system, there's a right way to do it and there's a wrong way to do it. And if you use the wrong algorithm, then you're going to have a bad time. One of the ways to do this wrong is to use what's called electronic codebook mode, or ECB. The basic idea is that your plaintext, when it's chopped up into these little segments, is fed individually into the cryptographic algorithm so that each piece of output is fully independent from the other blocks. This is a problem because if you have repeating patterns within your code within the plaintext, the problem is that your ciphertext is going to have those patterns repeat, and so you can tell, maybe you can't read the message, but you can tell that something in the message repeated. Even worse is now you're vulnerable to what's called a chosen plaintext attack, where if the attacker is able to get the victim to put a piece of message into the plaintext, then they're able to see predictably what the ciphertext is, and that can lead to discovering different things about the message, or even ultimately cracking the key. Anecdotally, this is what was used during World War II when the Allies were trying to crack Axis submarine codes, where they determined that there's a repeating part of the message that happened at the end of every message, and so based off of that, they were able to reverse engineer the code. I don't know if that's actually true, and I've never been able to find anyone who's been able to tell me definitively one way or the other, but it gives you the basic idea, right, that if you know that a particular part of the message is going to be the same, you can figure out what the ciphertext is, and from there you can figure out other things. Bottom line, you should never be using ECB mode. Now obviously ECB has its weaknesses, and so cipher blockchaining, or CBC, came about as an answer to this. So instead of starting with just a key and with just a plaintext, we also introduce something called an initialization vector, or an IV. The idea is that this is a random chunk of data which is sent along with the ciphertext. And what happens is when you do that first segment, that first encoding of a block, you pass in the initialization vector along with the plaintext and key, and together all three come up with the output. Now then the output of that first block effectively becomes the initialization vector of the next function, so that output 1, plaintext 2, and the key are what contribute to output 2. So even if you have repeating patterns within your plaintext, it doesn't matter because you've effectively seeded randomness in there, and you won't have that obvious repeating pattern within the ciphertext. Now, unfortunately, the answer isn't simply to just always use CBC, because the fact of the matter is there are other encoding schemes that can be used that also provide protection against chosen plaintext. And unfortunately, CBC has been vulnerable in the past to some bugs in implementation. And so it's actually being phased out of a lot of applications and protocols. For example, Transport Layer Security, or TLS, phased it out after the Lucky 13 attack became public. So really, the correct answer is to say that depending on what you're using, you need to check to see what your industry and your particular domain recommendations are. It's going to vary depending on the exact technology that you're using and exactly what you're using the technology for. A stream cipher is used for places where instead of encoding the plain text into ciphertext in blocks, we're doing it continuously. So first, a key is transformed into a key stream, which is just a continuous stream of bits generated from the single key. Plain text is then encoded one digit or bit at a time rather than in blocks. RC4 is one of the more famous stream ciphers. It's also famous because it's pretty insecure and there were problems with it. So it's something that shouldn't be used today. I'm not going to get into too much detail here because a lot of the focus on compliance is on block ciphers, but just know that if you are using a technology that utilizes stream ciphers, there's the same kind of issues as with a block cipher where you need to have whatever implementation or whatever mode is secure for that particular application and that particular use case. Asymmetric key encryption is a relatively new technology created within living memory. Essentially, two parties hold two keys, a private key and a public key. The public key is widely distributed and often signed by a trusted third party. In the case of a website, you get a digital certificate from a certificate authority showing that the website is in fact the organization that they say they are, so that when the client trying to reach out to the website can verify that that certificate is in fact authentic. Now, the way this works is, again, following the website example, someone trying to buy from an e-commerce site will get the public key for that site, encrypt a message, send it to them, and then they will use their private key to decrypt the message so that they and only they are able to read it. And this essentially is how the modern internet works, because with email that's encrypted, with websites that are encrypted, you're using asymmetric key encryption to initiate that secure communication without having any prior coordination with those organizations. Essentially, it allows two strangers to just walk up to each other and exchange information securely without any prior coordination to the effect. It's a wonderful technology, and we couldn't have the modern internet without it. HTTPS and SSH both rely on asymmetric key cryptography to allow two parties that haven't communicated previously to do so in a secure manner. Communication is initiated with the server using the server's public key, where the server will supply the public key, and usually it'll be signed. And then the client will, in their response, also supply a public key, which the server can use to respond. Now, in the case of a just random person using a web browser over the internet, there isn't really a signature proving that they are who they say they are. That's the whole point of authenticating with a username, password, two-factor, etc. But in a more secure environment, often the client will have a signed public key that proves their identity. Now, once the two parties have engaged communication, the HTTPS and SSH protocols will then switch to a symmetric key by exchanging key information, and essentially the protocols will come to an agreement on what symmetric key should be used. The math just involved for asymmetric key cryptography is computationally expensive, so it just makes sense to switch to using symmetric key cryptography. This is why when you're setting up SSH configurations, there's a symmetric key cipher mode, and this is essential for making sure that when you do switch to AES, you do so in a secure manner. All right, let's try actually encrypting something. So what we're going to do is fire up our good old friend OpenSSL again, and we're going to tell it to encrypt using AES. So that's that symmetric key with a key length of 256 bits. and we're going to use Cipher blockchain mode. Now for our password here, we're actually using a passphrase. So in a perfect world, you actually want to have a unique key of 256 bits, but you can't really remember that. It's just not really practical. So often what will happen is you'll supply a passphrase, which will be then expanded out to the actual 256-bit key. We're then using the test file that we created before and spitting out this output file here. So when we tell the algorithm to run, we can see the key that was generated from the passphrase and the initialization vector. Remember, the IV is the thing that's fed along with the key and the different blocks of the plaintext to produce the ciphertext. So if we actually try to read the file that we produced, it's just garbage. We can't read anything. So let's try decoding it, where in this case we pass in the same arguments where we're using the same algorithm, the same passphrase, but instead we're using this -d flag here to show that we want to decrypt it and produce this decrypted file. So then when we read it, we can see our original message. Now it's important to note that there are some better flags we can use. Like for example, OpenSSL is very helpfully telling us here that these flags would be better. But you know, at least for illustrative purposes, for the basic algorithm, you can see how OpenSSL is able to do this work for you. Now say you're a software developer and you actually need to encrypt something somehow for some reason. Now in a perfect world, you don't want to be doing this directly. There's a saying, don't roll your own crypto. And strictly speaking, this saying applies to don't try to create your own algorithm. Like AES is a great algorithm. It's very well vetted. Don't just try to write your own. That's goofy. However, by the same token, you don't want to try to encrypt your stuff by hand with AES, even using a library, because there's ways to use those libraries ineffectively and improperly. And so in a perfect world, you want to try to avoid that entirely, like use something else that's encoding the information and encrypting it the way that it needs to be set up, so that you as the programmer don't even need to get involved in that process. And it just sort of removes the opportunity for you to fail there, because failure in this case can be catastrophic. Now, say you can't get around it and you do need to actually encode something and encrypt it appropriately. So in this case, it kind of depends on the language you're using. If you're using Java, Java has some nice built-in capabilities that make things a whole lot easier for you, where, for example, the Java cryptographic architecture and Java cryptographic extension make it nice and easy for you to figure out what's well-vetted code and libraries that you can use, and they provide a lot of information on best practices on how to use them. In contrast, you have languages like C++ where not so much, where there are a lot of open source libraries. Some of them have been vetted, some of them have been independently validated, some of them not so much. And so it really is going to depend on what the application you're using, because depending on what industry you're in, there may or may not be requirements on what level of validation all of your open source is using. So it's really something that you have to be cognizant of. You can't just sort of pick something you found on the internet that it looks like it'll work. You have to look at it from a regulatory compliance perspective as well. Let's finish up this episode with a little bit of fun on the red team side. So say, for example, you're doing a pen test and you have some hashes and you're going to try to crack them. There's two main programs that get used for this purpose, John the Ripper and Hashcat. And there's two different ways that you'll go about this generally. Either one is you're supplying a word list when you can narrow down roughly what the password is, or if you have absolutely no idea, you just go for brute force. Now with a word list, you can either use a static word list, which is just a set of known commonly used passwords, or you can generate one based off of things that you know about your target and suspect they might be using for their password. Now, when we get into password security, we'll have a whole episode on this. We'll talk about tools and techniques that attackers will use to try to limit the scope of passwords that they can test for. And we'll also talk about, from the blue team side of things, looking at the techniques that they usually use and knowing what some of the human weaknesses are for how we generate passwords. There's ways to sort of foil this. Now, a bit of capture the flag hint. If you're doing a challenge where you're meant to crack the hash, usually the password is within the RockU word list that comes bundled within Kali Linux. It's just sort of an industry convention that the vast majority of the time, if the hash is meant to be cracked, it's in that word list. Now, of course, if the attacker is forced to brute force the password, and as the blue teamers you want to shove them into this position, they basically need to set up a whole farm of computers brute forcing passwords until eventually the distributed network is able to crack it. This is very time consuming, and you want to make it as expensive for them as possible. Now we're going to actually try doing a password crack. So if we remember that password hash from earlier that we created as an entry for a Linux etc password file, we're going to say that we got that hash somehow, and we're going to try to crack it. So we fire up John, and we give it the word list rocku. Now John is going to automatically detect the hash type and then try to crack it using this word list that it has. So it'll just iteratively go through the word list until it finds something that works. And we can see in about a nanosecond it came back with pass123 as the password. So if you have a good word list, you can burn through these hashes really quickly, but the trick is, of course, getting that word list. And so from the defender side of things, you want to make it so that the attacker can't do this and can't reasonably get a word list that generates your password. With more of these introductory concepts out of the way, for our next episode, we're going to take a step back and look at the bigger picture again. We're going to look again at some of the objectives and goals of an attack, as well as who some of the threat actors are and how this informs our defensive posture.